Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we'll be continuing our discussion on the motion of a top. And so far we have seen two types of motion of the top. One is the motion around the fixed axis, and the other is the motion around the moving axis, which is moving along the fixed axis. Right? So we saw in the previous module, we saw that these types of motion, especially this precession is there are two types of precession. One is the slow and the fast one. So let us look at these concepts using an example. So the example that I have is that of a simple top. A top is made by sticking a light pin of length 3 centimeter through the center of a uniform circular disc of mass m and radius 8 centimeter. Find the rates of slow and fast precession of the top when it is given a spin of 10 rev per second. Okay, and further the detail is given that alpha, the angle alpha, which is the spinning angle, is the precession angle is small. So we can effectively take alpha to be 0. Okay, so this is the case where we have attached a pin with a circular disc, right? So this is a disc attached to a pin, and the disc, we have to figure out what are first the moments of inertia of the disc. We are aware that for the disc the moments of inertia are, so MOI, the principal moments of the discs are 1/4 ma square, and of course along any diameter it has to be 1/4 ma square, and along the perpendicular to the diameter it is ma square, right? And then using parallel axis theorem, if we were to find the moment of inertia about the pivot point O, so this is a pin and it is given that the pin has length, let us say the length is h, and h is given to be 3 centimeter here. H is given to be 3 centimeter. So by parallel axis theorem, we see that the moment of inertia about the pivot point O, will be this moment of inertia, which is half. So this is going to be, so all the moments of inertia will change. So we have that moment of inertia about the diameters are A and B, and about perpendicular to the diameter is C. So we have A is equal to B is equal to ma square by 4 plus mh square, right? And this is the first result, and the second result is C will be half ma square plus mh square. Okay, so then We plug all the details. We are given this the spin of the disk, that is n to be 10 rev per second. So 10 into 2 pi radians per second. So this is 20 pi radians per second, and alpha equal to 0. So alpha is roughly equal to 0, and we have a quadratic equation for this setup. Well, we go back and look at we plug all the details a, b, c, n, alpha in our quadratic equation number. Well, where are we? So we had developed a quadratic equation for omega. So here, equation number 3. So in quadratic equation number 3, we plug everything, we get a solution. Omega fast is coming out to be roughly 79 radians per second, and omega slow is 1.52 radians per second. Okay, so that's what we wanted to find from the problem. So that's what we do. Okay, so now we are going to look at the motion of the top when it is from the axis which is fitted with the body of the top, right? So we are looking at so-called the Lagrangian dynamics. The Lagrangian dynamics of the top. Okay, so to study the Lagrangian dynamics, we have to look at the motion in Euler angle set. So we look at the Euler angles now. So now we have to precisely define what angles are these three Euler angles: theta, phi, and psi. So we have one axis which is precessing. So the top is precessing about a fixed axis. So this is k, and then the top is also. So here is the axis of the top. The top is also swiping. So this is so it is making an angle theta here with the vertical axis. So this is our top axis, which is a bar, and then it is also being swiped. So this is being swiping. So along the plane of motion, the angle which is swiped, the angle, let us say this is not the plane of motion, the plane is, this is the plane of motion. So we have x, y, and so here is my x, y. This is the projection of the top, and it is swiping an angle phi. And then finally, we expect that so now we will see that there is one more motion of the top which we haven't considered so far, and that is the top is further, the so-called so the top itself is now in this body fitted frame A prime. The top also is moving up and down. So which means that so the top is going to precess, let's say precess by an angle so-called psi. So let me try and explain. So one is the motion of the top which is moving around the cone. The other is the motion of the top which is, the other angle is explaining the swipe angle of the top. The first angle is explaining the tilt of the top, and then there is also the so-called an angle with which the top is fluctuating about its axis of rotation, and we call, later on we will denote this fluctuation as the so-called nutation. Not mutation, but nutation with an n. So then so what we have is, so these are the set of generalized coordinates for the rotational motion of the rigid body. Motion of the rigid body. Okay, so this is suitable with axial symmetry. This is suitable for bodies with axial symmetry. With axial symmetry. Okay. So then let us now further say that there is a point on the top. We denote that point is A. So let A be a particle on the top, on the symmetry axis. So point or particle on the symmetry axis, we call this as my symmetry axis. Symmetry axis. On the symmetry axis. Okay, so then let psi be the rotation of the body, the rotation of the body around the symmetry axis, around A. So it is this fluctuation that I was talking with respect to the symmetry axis. So rotation. Not fluctuation, but the rotation about the symmetry axis. So what we have is this precession, and then there is also with this axis, it is also rotating. So there is multiple motions. So within the symmetry axis also it is rotating, and it is also swiping this angle about the fixed axis. Okay, so it needs a little bit of visualization as to what are these complicated motions of a top. So then we are going to write down the energy formulation of this system. So since this is a holonomic system, we are going to solve this system on the Lagrangian frame or the moving frame. So holonomic system on the Lagrangian frame. So the kinetic energy is given by T is half a theta dot square plus half a phi dot sine theta whole square plus half c psi dot plus phi dot cos theta square. So what have we got here? It is this angle along the symmetry axis, it is rotating. So the net rotation is psi dot plus phi dot cos theta. So there is a rotation with respect to the fixed axis, and then there is a rotation with respect to the moving axis. Okay, so these are the various quantities. And then we have V, which is mgz. And so mgz implying the vertical distance from the xy plane, and this is going to be mgh cos theta, and the Lagrangian is given by L, which is half a theta dot square plus half a phi dot sine theta square plus half c psi dot plus phi dot cos theta square. So this is my kinetic energy minus the potential energy mgh cos theta. Okay, so then so notice that in this Lagrangian there is no no phi or psi. See, the only variables present in this Lagrangian are theta, theta dot, and phi dot and psi dot. So phi and psi are missing, which means the corresponding variables phi and psi are cyclic. So which means the corresponding generalized momenta p phi and p psi will be conserved according to our results earlier, right? So then, so since we saw that phi and psi are cyclic, we see that p phi and p psi are partial L partial phi dot and partial L partial psi dot, right? So what we have is that if we find this function, we see that this is a phi dot sine square theta plus c psi dot plus phi dot cos theta. right? And then this is sine square times cos theta itself. So, and then the other variable p phi is c times psi dot plus phi dot cos of theta. So we can take both these variables as Lz and Ln. These are my constants. These are my constants, and so again, as we can see, the phi 1 is the z component, of the angular momentum, and Ln is the spin component of the angular momentum, the spin component, or the spin or the axial component, of the angular velocity. Okay, so then if we were to write the conservation principle, we see that T plus V, the kinetic plus potential energy, is the total energy. And similarly, we can write down, we already have the Lagrangian. Instead of the Lagrangian, we write the Hamiltonian, set it equal to E. This is a conservative system, only weight is acting. And so I'm not writing, but this is straightforward. So this is, let me call this result as 2. Our first result is, this is my first result, let's call this as 1. So this is my Lagrangian. Okay, so then what we have is, suppose now we have, so what have we got? So this is, my 1 was not this, my equation 1 was this conservation principle. So I call these two equations, p phi equal to constant, p psi equal to constants, are my equation 1. So this is my conservation of angular momentum, and this is the conservation of energy, right? So these two, so we have three variables, psi, phi and theta, three Euler angles. And now we can see there are three equations or three conservation principles, and these three equations are sufficient to describe the motion. So these are sufficient to describe the motion of the top. So then, suppose now let us try to eliminate some variables. So from 1 and 2, suppose we eliminate phi dot and psi dot, right? So we see that a theta dot square is 2e. So we have eliminated two variables. Our final equation looks as follows. This is minus cn square minus Lz minus cn cos theta whole square by, this is not a complete denominator. So divided by a sine square theta minus 2 mgh cos theta. Right? So now we can rewrite this. So this is an equation only for theta. So this is a first order ODE equation. So the ordinary differential form of theta is given by theta dot square is equal to f of cos theta a sine theta whole square. So this is my star. Okay, so then let me call cos theta to be u. So let us say, so this my numerator is as follows. So u is our cos theta. So this is a times 2e. Well, we have taken a least common multiple, LCM. So a times 2e minus cn square times 1 minus u square minus Lz minus cn of u whole square minus 2a mgh times u 1 minus u square, right? And then, so now what we have is, it turns out that the left hand side of this equation star is theta dot square. So we expect that since the left hand side is everything is in real plane, the left hand side is positive, so we expect the right hand side is also positive. Now the denominator of the equation star is positive, so we expect the numerator f cos theta is also positive. So the conclusion is that f cos theta has to be positive, has to be positive. So that is what the theta values have to be set such that f cos theta is positive, so that the sign convention of this equation star is satisfied. Okay, so then what we have is that suppose the maximum or the minimum of theta occurs at when, of course, the derivative of f theta is 0. So if the maximum or the minimum of theta occurs when f prime theta is 0, so then if we were to plot, let's say, f of cos theta, so f of cos theta will so f of cos theta will be see cos, well, just a minute. So what we have is, if we look at f of cos theta, this function, let me call this as double star. This particular function is a cubic polynomial in U. So which means that f of u, if we were to try to find the roots, there will be 3 roots of this polynomial, right? So something we will use. So f of u is cubic, so 3 roots, and also you will see that as u goes to infinity or minus infinity, then f of u also goes to infinity or minus infinity. And we further see that f of 1 is minus Lz minus Cn square. If we plug cos theta equal to 0, we get this. And f of minus 1 is another negative number. So Lz plus Cn whole square. This is also negative. So what we get is minus 1 and 1. So f of z, and so we will have, let's say this is the case where we have the following, that the cubic polynomial f of u looks like as follows, right? So so we see that both at minus 1 and plus 1, f of u is negative. So this is negative, negative, right? And then what we see is that suppose we were to find any f of theta. Now, how do we know that? So it turns out that one of the roots, the third root of one of the roots of f of u will be greater than 1, right? So why? Because we see that, so suppose we take any angle theta, so theta lies between 0 to pi, and theta dot is 0. So theta dot is not 0 at t equal to 0. Then we see that cos of theta has to be positive, right? So cos of theta attains these values in between. So if theta naught is one value, then f of cos theta naught will be somewhere in this range from negative to positive, right? So then u will be oscillating, so which means that our u min, so if we have this well, so it turns out that the third root, which is this one, let's say u star, this is not possible because cos theta is between minus 1 and plus 1, so that cannot be greater than 1. So this is unphysical, this is not possible. So any root will be between, let's say, u min and u max, right? So theta naught is such that u is between u min and u max, and the third root u greater than 1 is not possible. That's not possible. Okay. So what is the conclusion out of this whole exercise is that if we were to solve the theta equation given by star, we are going to see that the solution is going to oscillate between u theta min to u theta max, because it is a trigonometric function. The solution will be periodic. So we expect that this period of oscillation of the solution, periodic oscillation, and this is when cos inverse u min is between u min and u max, right? So theta lies between u min and u max, which means so what exactly is theta? Going back to the diagram, we see that theta is doing a periodic motion. So what is happening now? So this particular periodic motion, we call this as nutation, right? Nutation with an n. So we have listed 4 types of motion of the top. One is the motion around the fixed axis. The other is 3 motions. One is the motion around the fixed axis. One is the motion of the rotation of the moving axis. And the third motion is that there is a periodic motion of the moving axis itself. And this periodic motion is the so-called nutation. The range of this nutation is between this range which I have listed here. And so this is I call it as nutation. Okay, so let us look at this idea with some example. So the example I have is, suppose a top is released with its axis at rest and making an angle of pi by 3 with upward vertical, making an angle of pi by 3 with upward vertical, right? So we have to find f of u. So find f of u, and for the case Cn whole square equal to 4amgh, we need to find the range of theta, the nutation range, right? So now let us see what information is given in this problem. It is given that initial angle theta naught is pi by 3, and of course the initial speed is released from rest, so the initial speed is 0, and of course phi dot is 0 and at t equal to 0, right? And of course psi dot here is not known, so this is unknown in this problem. In this details are not given. And so what we have is, so LZ comes out to be half Cn, and my energy, if we plug in all these details, this initial information detail, our energy comes out to be half Cn plus half mgh, right? And then my f of u is 1/4 1 minus 2u 4 amgh 1 minus u square minus Cn whole square 1 minus 2u, right? So we have that Cn square is 4 amgh. So this is my f of u, and for this condition Cn square is 4 amgh, we find that f of u comes out to be 4 amgh 1 minus 2u times 2 minus u times u. Okay, so we have u. So there are 3 roots of this f of u set to equal to 0. We will get 3 roots. U is half, u is 2, and u is 0. And of course we can neglect u equal to 2, and we see that corresponding to half we have theta equal to 60 degrees pi by 3, and corresponding to 0 we have theta equal to pi by 2. These are the cos inverse of these angles, of these values. So my nutation ranges from 60 degrees to 90 degrees. Okay. So that is what we have. So then if we so let us so this is the end of the problem, but suppose we also want to find the period. So the nutation range is given. Can we find the period? So to find the period, we have to go back and look at equation number star. So equation star, this one, right? So and we integrate this equation star for theta, and so for period we integrate theta, right? And for period we integrate theta, and we see that my period of nutation after plugging in all the values is 2 times square root a by mgh times integral pi by 3 to pi by 2 sine theta d theta, and then we're plugging in everything, 1 minus 2 cos theta, and then 2 minus cos theta. So we integrate this giant expression and we get the period roughly equal to 3.3 times the quantity inside the square root, which is a by mgh. A by mgh. Okay, so then so that completes this problem. So then we have we want to see again the precession about the axis of this top, right? So what am I looking? So precession of the axis. So precession means the rotation of the axis itself, the top axis. So we see that using the conservation principle of P phi, if we plug in all the values, we had a phi dot sine square theta plus cn cos theta. This is our LZ. And then at t equal to 0, we get theta equal to alpha, and theta dot equal to 0, and phi equal to 0, and phi dot equal to omega. And so these are my information, and for this we can plug in and find this constant LZ. LZ is a omega sine square alpha plus cn cos alpha, right? And then we plug this information for LZ in our top equation. So this is going to be, so we get that a phi dot is equal to sine square theta. A phi dot sine square theta is equal to a omega sine square alpha plus cn cos alpha minus cos theta. So after plugging in the value of LZ in our top equation, that is theta star, the star equation for theta. Now suppose we have, now we know that this is going to be a quadratic equation for theta, right? So suppose we expect that the roots are real, or the discriminant is positive or non-negative. So this is 4 AMGH. So this is the condition for real values of omega, right? So this is a condition where we have two real roots, and suppose suppose we set omega equal to omega s. Suppose we set omega is equal to omega s, which is the slow precession rate. So if my omega is less than omega s, we see that theta double dot is 0, greater than 0 initially. So if so what I am saying is, suppose we plug in the value of omega which is less than the slow root, the omega s, right? We will see that the solution we get is theta dot is positive. So what it means is that the angle theta is initially increasing. So, or in other words, it implies that when the top starts to rotate, initially the top falls and then it starts to rotate, right? So, so that is what we have. So it means that theta increases initially, it increases, and theta min is equal to alpha. So it increases and theta min is alpha. So the conclusion is initially the top falls. Initially the top falls, right? So it falls a little bit and then it regains and then it then it starts to rotate. So there is a quick fall, and if the eye can catch it, there is a quick fall and then eventual retention and starts to rotate. Okay, so then let us quickly go through an example. So the example says in previous example, in this example, so let me call this as example. Well, what have we got? Psi is, yeah, so this is my example, let's say A, right? So this is the same top example where we were finding the period. So in A, so from example A, suppose we want to find the angle through which the top precesses during one period of inclination angle theta. Okay, so find the angle through which the top precesses during one period of inclination. So we are saying that the top is going through angle pi by 3 to pi by 2. So that is a nutation angle. But during this period, when it goes from this angle to the other angle, we have to find how much the top has rotated. So if we were to solve the top equation, so the top equation was a phi dot sine square theta is equal to a omega sine square alpha plus cn cos alpha minus cos theta, and this is where alpha is equal to pi by 3, omega is equal to 0. The top is released from rest, so theta is equal to pi by 3 and cn square is equal to 4am gh. Right? If that is the case, then we see that phi dot is cn 1 minus 2 cos theta by 2a sine theta, sine square theta. Right? So so for equal roots we have this form, and now if we integrate this, so phi is integral 0 to tau phi dot dt. And then once we integrate our phi dot equation, we get cn by 2a integral 0 to tau 1 minus 2 cos theta by sine square theta dt, and this is going to be square root mgh by a times 2 times integral from pi by 3 to pi by 2 1 minus 2 cos theta by sine square theta d theta by dt, right? So these are while plugging, we are just now the period has already been found for one nutation, and this is, rather than using the period, we have used the angle information, and when we do that, we are going to find that the answer is roughly 1.69 radians, or this is equal to 97 degrees. Okay, so enough of details about the top. We have looked at various motions. Now we are going to look at, in our next module, we will look at another motion, or the so-called motion of a gyroscope. So thank you so far for listening.